Geometry main concepts, axioms. Euclid took an abstract approach to geometry and its elements, one of the most influential books ever written. Euclid introduced certain axioms or postulates, expressing primary or self-evident properties of points, lines, and planes. He proceeded to rigorously deduce other properties by mathematical reasoning. The characteristic feature of Euclid's approach to geometry was its rigor, and it has come to be known as axiomatic or synthetic geometry. At the start of the 19th century, the discovery of non-Euclidean geometries by Nikolai Ivanovich Lobachevsky, Janos Bolyai, Carl Friedrich Gauss, and others, led to a revival of interest in this discipline. And in the 20th century, David Hilbert employed axiomatic reasoning in an attempt to provide a modern foundation of geometry. Spaces and subspaces. Points. Points are generally considered fundamental objects for building geometry. They may be defined by the properties that they must have, as in Euclid's definition as that which has no part, or in synthetic geometry. In modern mathematics, they are generally defined as elements of a set called space, which is itself axiomatically defined. With these modern definitions, every geometric shape is defined as a set of points. This is not the case in synthetic geometry, where a line is another fundamental object that is not viewed as the set of the points through which it passes. However, there are modern geometries in which points are not primitive objects, or even without points. One of the oldest such geometries is Whitehead's point-free geometry, formulated by Alfred North Whitehead in 1919. Lines. Euclid described a line as breadthless length, which lies equally with respect to the points of itself. In modern mathematics, given the multitude of geometries, the concept of a line is closely tied to the way the geometry is described. For instance, in analytic geometry, a line in the plane is often defined as the set of points whose coordinates satisfy a given linear equation. But in a more abstract setting, such as incidence geometry, a line may be an independent object, distinct from the set of points which lie on it. In differential geometry, a geodesic is a generalization of the notion of a line to curved spaces. Planes. In Euclidean geometry, a plane is a flat two-dimensional surface that extends infinitely. The definitions for other types of geometries are generalizations of that. Planes are used in many areas of geometry. For instance, planes can be studied at a topological surface without referring to distances or angles. It can be studied as an affine space, which collinearity and ratios can be studied but not distances. It can be studied as the complex plane using techniques of complex analysis and so on. Curves. A curve is a one-dimensional object that may be straight, like a line, or not. Curves in two-dimensional space are called plane curves, and those in three-dimensional space are called space curves. In topology, a curve is defined by a function from an interval of the real numbers to another space. In differential geometry, the same definition is used, but the defining function is required to be differentiable. Algebraic geometry studies algebraic curves, which are defined as algebraic varieties of dimension 1. Surfaces. A surface is a two-dimensional object such as a sphere or paraboloid. In differential geometry and topology, A surfaces are described by two-dimensional patches or neighborhoods that are assembled by diffeomorphisms or homoomorphisms, respectively. In algebraic geometry, surfaces are described by polynomial equations. Solids. A solid is a three-dimensional object bounded by a closed surface. For example, a ball is the volume bounded by a sphere. Manifolds. A manifold is a generalization of concepts of curve and surface. In topology, a manifold is a topological space where every point has a neighborhood that is homomorphic to Euclidean space. In differential geometry, a differentiable manifold is a space where each neighborhood is diffeomorphic to Euclidean space. Manifolds are used extensively in physics, including in general relativity and string theory. Angles. Euclid defines a plane angle as the inclination to each other. In a plane are two lines which meet each other and do not lie straight with respect to each other. In modern terms, an angle is the figure formed by two rays, called the sides of the angle, sharing a common endpoint called the vertex of the angle. The size of an angle is formulated as an angular measure. In Euclidean geometry, angles are used to study polygons and triangles, as well as forming an object of study in their own right. The study of the angles of a triangle or an angles in a unit circle forms the basis of trigonometry. In differential geometry and calculus, the angles between plane curves and space curves or surfaces can be calculated using the derivative. Measures: length, area, and volume. Length, area, and volume describe the size or extent of an object in one dimension, two dimensions, or three dimensions, respectively. In Euclidean geometry, the analytic geometry, the length of a line segment can often be calculated by the Pythagorean theorem. Area and volume can be defined as fundamental quantities separate from length, or they can be described and calculated in terms of lengths in a plane or three-dimensional space. Mathematicians have found many explicit formulas for areas and formulas for volumes of various geometric objects. In calculus, area and volume can be defined in terms of integrals, such as the Riemann integral and the Lebesgue integral. Other geometric measures include the curvature and compactness. Metrics and measurements. The concept of length or distance can be generalized, leading to the idea of metrics. For instance, the Euclidean metric measures the distance between points in the Euclidean plane, while the hyperbolic metric measures the distance in the hyperbolic plane. Other important examples of metrics include the Lorentz metric and special relativity, and the semi-Riemannian metrics of general relativity. In different direction, the concepts of length, area, and volume are extended by measure theory, which studies methods of assigning a size or measure to sets, where the measures follow rules similar to those of classical area and volume. Congruence and similarity. Congruence and similarity are concepts that describe when two shapes have similar characteristics. In Euclidean geometry, similarity is used to describe objects that have the same shape, while congruence is used to describe objects that are the same in both size and shape. Hilbert, in his work on creating a more rigorous foundation for geometry, treated congruence as an undefined term whose properties are defined by axioms. Congruence and similarity are generalized in transformation geometry, which studies the properties of geometric objects that are preserved by different kinds of transformations. Compass and straight edge constructions. Classical geometers paid special attention to constructing geometric objects that have been described in some other way. Classically, the only instruments used in most geometric constructions are the compass and straight edge. Also, every construction had to be complete in a finite number of steps. However, some problems turn out to be difficult or impossible to solve by these means alone, and ingenious constructions using neosys, parabolas, and other curves and mechanical devices were found. Rotation and orientation. The geometric concepts of rotation and orientation define parts of the placement of objects embedded in the plane or in space. Dimension. Traditionally, geometry allowed dimensions: 1, a line or curve; 2, a plane or surface; and 3, our ambient world conceived of as three-dimensional space. Furthermore, mathematicians and physicists have used higher dimensions for nearly 2 centuries. One example of a mathematical use for higher dimensions is the configuration space of a physical system, which has a dimension equal to the system's degrees of freedom. For instance, the configuration of a screw can be described by 5 coordinates. In general topology, the concept of dimension has been extended from natural numbers to infinite dimensions, Hilbert spaces, for example, and positive real numbers in fractal geometry. In algebraic geometry, the dimension of an algebraic variety has received a number of apparently different definitions, which are all equivalent in the most common cases. Symmetry. The theme of symmetry in geometry is nearly as old as the science of geometry itself. Symmetry shapes such as the circle, regular polygons, and platonic solids held deep significance for many ancient philosophers and were investigated in detail before the time of Euclid. Symmetric patterns occur in nature and were artistically rendered in a multiple of forms, including the graphics of Leonardo da Vinci, M.C. Escher, and others. In the second half of the 19th century, the relationship between symmetry and geometry came under intense scrutiny. Felix Klein's Langen program proclaimed that in a very precise sense, symmetry, expressed via the notion of transformation group, determines what geometry is. Symmetry in classical Euclidean geometry is represented by congruences and rigid motions, whereas in projective geometry, an analogous role is played by collineations, geometric transformations that take straight lines into straight lines. However, it was in the new geometries of Bolia and Lobachevsky, Riemann, Clifford, and Klein, and sophists lie that Klein's idea to define a geometry via its symmetry group found its inspiration. Both discrete and continuous symmetries play prominent roles in geometry, the former in topology and geometric group theory, the latter in Lie theory and Riemannian geometry. A different type of symmetry is the principle of duality in projective geometry, among other fields. This meta phenomenon can roughly be described as follows. In any theorem, exchange point with plane, join with meet, lies in with contains, and the results in an equally true theorem. A similar and closely related form of duality exists between a vector space and its dual space.